Hello class. Today we're going to express the rate of a given reaction in terms of the variation in concentration of a reaction or product of that substance with time. We're also going to calculate the average rate over an interval of time given the concentration of a reaction or product at the beginning and end of that interval. The homework assignment that goes with this play posit is the quest Kinetics Instantaneous and Relative Rate. So we're going to start off today by talking about the different factors that affect the rates of reaction. I've got a bunch of different simulations that will help us reason through them. And we'll talk about instantaneous and relative rate. So there are four main factors that affect our reaction rate. We have surface area, we have temperature, concentration of our substance, and then we also have catalysts. When we're talking about rate, we're talking about how fast it takes the reaction to come to completion. We spent all of last unit talking about thermodynamics and whether or not things are spontaneous, but it's a good thing to point out that spontaneous does not always mean that it happens at a fast rate or at a reasonable rate. So we'll be looking at reactions that do in fact happen spontaneously, but they may not happen within a reasonable amount of time. So we want to look at reaction rate for that reason. So we have a couple of different simulations. With these simulations, this first one we're looking at effective concentration. If you had to guess, how might concentration affect the rate of your reaction? This is a good question that relates to our kinetic molecular theory. If we were to throw 0.5 molar in here, let's see what had happened. All right, off the bat we have a collision and it turns green, but it's taken a good bit of time for these things to come in contact with each other. All right, another one turns green. So this is a very low concentration. There's not that many particles in here, and they're not colliding with each other very much at all. Oh, there goes another. So with low concentration, you could expect low collisions, right? If we were to reset this and up the concentration, what do you think would happen? You would say there'd probably be more collisions. I'd agree. And right off of that, boom, look at that. We already have 3 that turn green. Oh, there's another. Actually, all of the blues that were there have turned green at that point, so that was real quick. Okay, so let's try that again. Notice there's only 5 blues over here. So we're measuring how quickly it takes those 5 blues to turn into greens. All right, 2 molar, boom. Oh my gosh. That was before you could even see it. Let's watch that again. Boom, super quick, right? So we can say that, I'm gonna click these arrows because look at that, awesome. As the concentration goes up, the reaction speed or the rate also goes up. They are proportional to each other. And this makes sense in terms of kinetic molecular theory or even just collision theory. The more particles we have in a confined space, the more likely they are to come in contact with each other, right? We also have the effective surface area. So here is a nail. We're going to look at this nail. All right. So as those particles bump into each other, it happens at, a decent rate. But as you saw, it started to slow down towards the end of that reaction because there wasn't as much surface area left for those particles to hit. Now, what would you expect to happen if we made the surface area larger? Well, you should have said the rate of reaction would have gone faster. And I agree, if we give this more surface area, then the particles have more things they can come in contact with. So let's look at it. Boom. Oh my gosh. Super fast. Look at that. We chopped up our nail into a bunch of little chunks, and that went really, really fast. So since more particles are now exposed to attack, it increases the chances of reactant particles colliding with them. Therefore, there are more collisions at any given time, and we get a faster reaction. It's pretty cool. The same can be said for any solutes that are dissolving in solution. So here we've got marble chips that are in acid solution. These are the same chips, but they're just a little bit larger. So smaller here, meaning there's more surface area. Here, these are larger, not as much surface area. So let's see what happens to our chips as they dissolve. And the nice thing is these graphs are beautiful. All right. So as these things dissolve, the mass of the solution definitely changes, or the mass of the chips, that is, changes. And it takes almost double the amount of time for this reaction with the larger chips to take place, because there's not as much surface area. When you break them into tinier chunks, it works a lot better. Okay. Here's another one. So we've got magnesium ribbon. So here's a big piece of magnesium ribbon. And it starts to burn. It's got a decent sized glow. Here's some powder. Look at that. There's actually a lot larger glow at first initially, but it all goes away in just about a flash. Let's see that again. So the powder has more surface area, and boom, and it's done. That was barely 2 seconds. This one, we've got a full, if I was to count, it's probably like 4 or 5 seconds at this point. Okay, so surface area. Surface area has the same relationship. As surface area goes up, the reaction speed or the rate also goes up. All right. Temperature. Temperature is our other factor here. Think about what temperature is. What is temperature a measure of? You should have said temperature is a measure of the average kinetic energy. When we're talking kinetic energy, we're talking about speed. So at higher temperatures, what do you expect to happen in terms of collision? There should have been more collision. I agree. So let's play this reaction at 30 degrees Celsius and this reaction at 40 degrees Celsius. There's a little bit of lag, I'm sorry. But look at that. The one at 40 degrees is already done, and I started it after the one at 30 degrees. The one at 30 degrees is still going. It's taking its sweet time. Oh, almost. Almost. I don't know if these things ever will collide. Good Lord. Oh, boom, there was one. All right, sweet. I don't know if we have time for all of that. Oh, really? Did you just see those two? They totally hit each other. They should have... Okay, whatever. Well, one day this reaction will stop. But you get the point. At 40 degrees, we have more kinetic energy, which increases the probability that we will collide with each other, which also increases the probability that we will react. So we'll talk about collision theory in a moment. I'm done with this. It's not stopping. It's going to keep going. We don't have enough time for that. Man, I've never seen it go this long before. Wait. Oh, what? It just hit again. What? Okay. I don't know if they're actually going to react at this point. Anyway, you get the gist. All right. Here's another one. We've got sodium thiosulfate solution. One's at 30 degrees, one's at 40 degrees, and they're being reacted with hydrochloric acid. And you can see that we added our drop, and the one at 40 degrees gets cloudier much faster. So again, same relationship. As our temperature goes up, reaction speed and rate also goes up. A lot of this is common sense. These are things we've talked about in honors, and we just haven't put it in terms of the kinetics for this unit yet. So these factors, they make sense, but when we start applying them to actual equations and doing the algebra to solve for these things, that's where it's going to start to blow your mind a little bit. All right. The last thing is a catalyst, and I was trying to show this to you in the last unit with thermodynamics. I couldn't get my my simulation to work. But here's a normal exothermic reaction, right? The reactants, here you go, the reactants are at a greater energy than the products, which means energy is given off. This is exo because energy is lost, right? Energy is lost. There you go. We know that this chunk here, this is our activation energy. Activation energy, oh, sorry, that's bad handwriting. Activation energy, they use the symbol E sub A, energy of activation. So this is for a reaction without a catalyst. All a catalyst does is lower your activation energy. So I'm going to erase this so you can read all that. Okay. And the activation energy is lowered with a catalyst, and we get a new activation energy here. So this is E of A. All the activation energy is the amount of energy you need to get the reaction started. So when we're thinking in terms of collisions, we need some amount of energy here to get us to the top of our hump. When we get to the top of the hump, we have a transition state. So we're going to talk about that in a minute. We're going to talk about a transition state. Sometimes they also call it an activated complex. When we have an activated complex, that means we are at a point where the reaction can progress. We have enough energy to keep moving, and more likely than not, we're going to move to form more products. So I'm going to show you what that looks like when we talk about collision theory a little bit more. Okay. Now, what we focused on last unit was enthalpy. This little chunk here, the difference between the activation energy, the difference between the reactants and the products, this is our enthalpy, the energy that's lost. So it's the difference between the reactants and the products. The activation energy is the difference between the reactants and the top of our little hump there. Okay. So, collision theory in a nutshell. With kinetics, we can have situations where it's just one particle. We also can have situations where we have three particles, although it's very rare that three things collide at one time. So when we're talking about collision theory, we're usually looking at two particles. So actually, I chose this background intentionally. We've got two particles. And it's nice because it actually compares, I'm going to move these words out of the way for a second. It actually compares the ineffective collisions to the effective collisions, which just proves the point that orientation is necessary. Having the right orientation, in simpler terms, they have to hit each other the right way in order for them to become activated or to become in that transition state. The reason why is they need to have enough energy to overcome the electron-electron repulsions, right? All of our atoms have electron clouds. When the clouds get close to each other, they want to repel, right? Negatives repel negatives, just like positives repel positives, right? Like charges repel. So if we have enough energy to overcome that repulsion, it actually can cause us to rearrange. And like I was saying earlier, we've got our transition state or activated complex. That is the collision product. So here, that's the collision product at the peak of the activation energy hump. So when you see an effective collision, this thing hits at that angle, and you get your reaction, and then we end up having our nice new products of NO2 and O2 in this particular case. When it's not successful, there are times where you can get to your transitional state and you are not effective, like here. When it hits that way, it's not enough for it to react. It just causes them to bounce off each other, and we end up, if I can minimize this, we end up as we were before. So collision theory in a nutshell. All right, sorry for all that mess. Okay, whoa, too far. So all of this is important because in lab we're going to start looking at reaction rates. So the nice thing is when we have a graph, we're typically looking at the disappearance of our reactant. We can also talk about rates in terms of the appearance of product, but typically we look at the disappearance of reactant. So with a graph, we typically have time on the x-axis and we have concentration in molarity on the y-axis. The nice thing is that when we graph this, the slope of a line that is tangent to the curve at any point is the instantaneous rate at that time. Yes, my friends that have taken calculus, tangent lines. That's exactly what I'm saying. So, if you were to take that point and draw a line tangent to that specific point, you could figure out the rate, the instantaneous rate at that time. Now, if you look at the curve, the steeper the tangent line, the faster the rate. So this reaction seems to happen fairly quickly, and then as it progresses, the tangent line is not as steep anymore, which means that the rate is slowing down. So it slows down towards the end of the reaction, which is interesting. We'll have to keep that in mind. There's something we'll look at with reaction mechanisms, and that will help explain why we have different rates throughout a reaction, right? We also have relative rates. So with relative rates, the stoichiometry matters and the sign matters. Since we're talking about reactant disappearance, it's typically negative because the reactant is decreasing. If we have product appearance, we're talking about a positive sign because we are making product. It's now appearing, right? It's coming into the fold. When we're talking about rates, it's usually the change in concentration of our reactant over time, but we can also relate it to the product and how the product is appearing over time. So that's why it's called relative rate, right? We want to look at these things in comparison to each other. So let's do our first example. It says, what are the relative rates of change in concentration of the products and reactants in the decomposition of nitrosyl chloride, which is NOCl? So as we said, the stoichiometry matters. How many reactants do we have here? Just one. Okay. So we've got our rate. Our rate is going to be equal to, we said reactants disappearing is negative. So negative delta, which means change of my concentration of NOCl. And that's going to be proportional to my coefficients and my rates, right? So 2 times delta T. All right. Now that is equal to my products that are forming. So I know that my products are going to be positive. So it's the change in concentration of NO. And it is the same proportionality as the previous one because we have coefficient of 2. Now that is also equal to the change of concentration of my chlorine gas. Now this one only has an of a coefficient of 1, so we've got delta T. Okay, so if we were to express the rate for this reaction, any of the three would be valid. Typically, we look at this one here because it's the reactant disappearing, but this is the format that you would typically see. Whoa, there you go. So it says initial rate of reaction. This is exactly what they had in the book. Now, I kind of simplified it a little bit. They put 1/2 in front of their numbers, but that is the same as putting 2 on the denominator. It means the same thing. On that first quest, you'll have to look at these relative rates. Just know that the coefficient is what goes on the bottom in respect to time. Okay? And I think that's it for this first one. Sweet. Have a great day.